Thank you for watching for this video. This is Shunsuke Aoki, a researcher at Carnegie Mellon University, and the work is collaborated with Toyota R&D Infotech Lab. The talk title is Cooperative Perception with Deep Reinforcement Learning for Connected and Vehicles. And this talk is for IEEE Intelligent Vehicles Symposium 2020. In this talk, we present a resource-efficient cooperative perception framework for connected vehicles. Let me introduce the cooperative perception concept first. In cooperative perception, each connected vehicle shares the sensor data over vehicular communications. By sharing the sensor data among multiple vehicles, we can get the information from the blind spot, and this enhances road safety. In particular, the cooperative perception is useful for road intersections because vehicles come from different directions and vehicles' collision may happen. For example, in this figure, vehicle A cannot see vehicle D by using the local sensors directly, but other shown vehicles can tell the presence of vehicle D by using cooperative perception. Currently, ETSI, European Telecommunication Standard, is now working for the standardization for cooperative perception or collective perception. One practical issue for cooperative perception is huge data traffic for vehicular communications. For example, in traffic jam, many connected vehicles broadcast the same information, and it leads to packet collisions and packet losses because the network resource is so limited. In fact, there are a few studies for saving network resources, which includes the data processing level and data selection approaches. One of the most significant issues for data selection in cooperative perception is the difficulty to know which data are beneficial and which data is helpful for the potential receivers. First of all the receivers may have the data for target objects from their local sensors, but there are no ways to know whether the receivers have such information. Also, there are many factors and elements to determine the situation, including relative locations and network loads. In addition, of course, the network resources of vehicular communications are limited, and we have to save the resources in order to avoid packet collisions. For example, in the right figures, cooperative perception may be helpful for the upper cases, but it doesn't have beneficial for the lower case because the vehicles can detect each other by using the local onboard sensors. Based on these motivations, in this work, we develop a practical, reliable, and resource-efficient cooperative perception framework by presenting two ideas: sensor fusion framework for avoiding rumors and deep reinforcement learning for data selection. Here is the outline of this talk. We have already covered our motivation. We will present a resource-efficient cooperative perception, including system model and deep reinforcement learning model, and then we will present an integrated simulation platform that uses multiple open source software. Let me present the system model first. For the resource-efficient cooperative perception, we use the cooperative perception message, which is also called CPM, to store the data for detected object information, such as object types, location, and heading. At the same time, along with the V2X communications, vehicle to everything communications standard, we assume each connected vehicle broadcasts BSM, basic safety messages, as a safety beacon. This BSM includes the transmitter's basic information, such as location, speed, acceleration, heading, and vehicle sizes for improving road safety. These CPM and BSM are transmitted over wireless communications, vehicular communications, from vehicle to vehicle. Here in our system, CPM information are not relayed, not multi-hopped, in order to avoid spreading unreliable information, which might be called rumor. The right figure represents our sensor fusion framework. Each connected vehicle has the input from camera, LiDAR, and radar, and V2X communications by CPM and BSM. But we do not put the information from V2X for cooperative perception messages in order to avoid rumor spreading. Connected vehicles just share the information from the local onboard sensors. Here we give the overview of our deep reinforcement learning framework. In this work, To anticipate the value of information for the potential receivers, we use the deep Q-learning that is able to accommodate many factors such as relative locations and network loads. In Q-learning, agent can update its policy in an interactive environment, and action, state, reward, these three components should be designed and tuned. Here is our usage of Q-learning. Each vehicle has its state, and there is an interactive environment. Here is load networks and other vehicles in the simulated world. Each agent takes actions at each time step, sending the cooperative message or not. By taking the actions, the agent gets the reward from the environment. We can design the reward function to encourage each vehicle to use the vehicle networks efficiently and reliably for cooperative perception while enhancing road safety. One feature for the Q-learning is Q-table that identifies a reward associated with all the state and action pairs. Since there are many possible state action pairs for cooperative perception, we use the convolutional neural networks, CNN, to determine the action of each connected vehicles. Also, since we consider the pair of state and action, the state and action should be represented as fixed length vectors. For improving the performance of Q-learning, we have to carefully design the state and reward function. Let's see the design for state and reward a little bit deeper. First of all, for state, we have to store relevant information for vehicles, including relative occupancy and network congestion levels for vehicular communications. Again, the state should be a fixed length vector. For occupancy, we split the field of view of local sensors into grid and give one class for each grid, from empty, occupied, and occluded. Also, since the network congestion level is directly related to network reliability, we define and use the congestion levels for state. For reward function, we have one incentive and two penalties. When the receiver gets the information for undetected object in cooperative perception, the reward is given because this behavior helps to improve road safety. On the other hand, when the known object for the receiver are shared in cooperative perception, the penalty is given, which is negative value for reward, because this behavior just wastes the network resources. In addition, when the network around the receiver is congested, the penalty is also given. By using these state and reward, the vehicles keep learning the action to be taken. Let us move to the next topic, the integrated simulation platform that includes 3 open source software. To evaluate the performance, we developed simulation environments where we combine 3 different open source software, Sumo, Kara, and Yoro. Here in this figure, yellow boxes are existing open source software, and blue ones are Python tools that are also open in GitHub. First of all, Sumo generates mobility data, and the generated data are used for V2X simulation and vehicle simulation in Kara. Kara provides realistic 3D graphics and sensor models that are essential for testing vehicles' perception. The sensor data taken from Kara are processed with Yoro object classifier. By using these realistic sensor simulation and object classifier, each connected vehicle may not detect objects that are partially occluded. And after processing these data, our deep reinforcement learning framework determines which information should be transmitted. To keep the consistency between Sumo and Kara load networks, we also developed Sumo Kara bridge by using this Sumo Kara bridge, and these 2 figures are the load network for Sumo and Kara. They are consistent. For the evaluation, we prepared for 2 load networks, and one is used for training for CNN neural networks, and the other one is used for testing. In baseline protocol, each connected vehicle always broadcasts CPM, cooperative perception messages, whenever the local perception detects moving and static objects on public road. The first result is the average number of data in cooperative perception message, when we change the number of vehicles running in the simulation world. That is to say, x-axis describes the vehicle density, and y-axis means the traffic in vehicle communications. The baseline protocol monotonically increases the data volume in vehicular communications, but our reinforcement learning-based protocol mitigates the traffic volume. In addition to that, when we consider the packet collisions and packet reception ratio, our protocol can increase the reliability by increasing the training time. Here, y-axis means the success of packet reception, and larger value is good, and x-axis means the training time. Therefore, it turns out that our approach successfully mitigates the network load in vehicular communications, and it improved the network reliability. To wrap up here, by developing the sensor fusion framework and deep reinforcement learning framework, we successfully designed and developed reliable cooperative perception framework. Let me conclude this talk. We presented a resource-efficient cooperative perception framework with deep reinforcement learning. Also, to test our cooperative perception framework, we integrated multiple open source software, Sumo, Color, and YOLO, to account for the realistic mobility model, realistic vehicle model, realistic sensor model, and image classifier. Finally, our evaluation shows that our approach saves the network resources and provides higher detection accuracy and network reliability. Thank you very much for checking this video for IEEE Intelligent Vehicle Symposium in 2020. Please feel free to contact us for any questions and feedback.